row echelon. Do they use row? They're not doing row reduced, right? Yeah. Echelon form. It's called row echelon form. So when you can get this kind of diagonal here, like this, with zeros underneath, you are in row echelon form. So would you like to see me work this one? You just do the same problem we just did, just leaving it as a matrix the whole way. You want to see how it would? You want? Yeah, let's do it. Okay, but I'll move quick. Look back because you have your notes. You know what we did. What was the first thing we did on this? We multiplied the third one by -2. So I multiply this by -2. Now watch. This now becomes, I better stick with the black one. That one becomes a new matrix. 1, 1, -1, -1. 4, -3, 2, 16. And then -4, 4, 6, -10. That's my new matrix, right? And now add the second and the third together, replace the third with that, right? So my new matrix is going to look like this. It's that exact thing, right? Nothing changed except the last row is going to be what? 0, 1, 8, 6. Are we in row echelon form? Not yet. We need a 0 here and a 0 here. So I now multiply what? What do we do? The top one by 4? By -4, right? Top one by -4. Go across. It becomes -4, -4, +4, right? +4 there. I know I'm going quickly here because I'm reusing my same matrices.
So add together, replace the second.
Add together, replace the second one. Is that all right, everyone? That was -4 through the top one. Now I'm going to add these two together and replace my second one there, right? And I'm going to do something else that I didn't do before. I'm also going to divide that -4 back out in the same step. So I'm adding these two together. What does that create here? What does that create for my second? 0, -7, 6, and 20, right? But then instead of writing -4, -4, 4, 4, I'm going to divide through by -4 again, and that would take me back there.
Yes, sir.
Now multiply the bottom one by 7.
So you divided out the 4 from the just
-4 from the top one. Just because I want to get back to ones because I like small numbers. So 7 through here, right? So here's where I am now. One, 1, -1, -1, 0, -7, 6, 20, and then 0, 7, 56, 42. Add these two together and replace the last one with it. Yep, which is going to be 0, 0, 62, 62.
Boom, echelon form.
That's it. That's echelon form. I know I moved quick there, but this is on video. You can go back and watch it if you need to. All right. So this right here is what we wanted, right? And now what we would do is we just think about what happened. Look, I could take this row right here and divide everything by 62, couldn't I?
Yes.
So that would turn this into a 1, 1, wouldn't it? And at that point, you're saying z is 1. So if we come back in, if we were to fill everything back in, this is z, this is z, this is z. This is y, this is x, this is y, this is equals, equals, equals. Do you see it's all the same, just different notation? Do y'all see that? Okay. Now, matrices become a little more than just this later, okay? It's not, I'm not telling you this is all a matrix does or all it's useful for. Because someone could argue, well, I don't even need to do that. Just leave the x's, y's, and z's in there and I don't care. It's fine. But turns out later that matrices can be multiplied together and added together, and it gets a little more involved. All right?
Like that's a later class.
It is later. It's linear algebra. Now, let me ask you something. I'm going to erase this. Is that all right? I'm not going to do the back substitute because we already did that. All right. What if you had a matrix that says this? What is the solution? So what if I give you this? I tell you, hey, I've got this matrix. It's an augmented matrix.
Okay, so 5, 3, -4.
Yeah, what this last equation tells you what? Z is -4. And this one, because these are both zeros, right, tells you 1y, right, equals 3. Doesn't it?
Yeah.
So y is 3. And this one tells you what?
X is 5.
X is equal to 5. Now, getting a matrix into this format, notice that we have the little triangle here, but more than that, we actually have a triangle this way too, right? And we've got ones along the diagonal. Yeah?
Yeah.
This is hard to get to, all right? But if you're able to get to this, then you have all the answers just sitting there looking at you in your face, right? This right side are your answers. This right here is called reduced row echelon form. The other way was called row echelon form. This is reduced row echelon form. Reduced row echelon form. Okay. All right. How many of you have your calculators with you? Anyone have? Let's take a show of hands. Yeah? Graphing calculators? How many of you have graphing calculators? Yeah? Pull those out. You paid a lot of money for them. That's not the one. Sorry. Graphing somewhat? That want to work? Okay, if you don't have a graphing calculator, this won't work. All right? You're just going to have to stand by because I'm just showing this to people so that they know it's there, right? If you're going to go on and do more math. So look, in most of these graphing calculators, you have a function built into the calculator called reduced row echelon form. It will actually take a matrix and turn it into this for you. All right? And I want to show you how to do that. You ready to see it? Y'all don't look too excited, okay? I'll take you step by step on how to do it, all right? But I'd like to do it with the problem that we had earlier. Here it is. So I want us to solve this. It was 1, 1, negative 1, negative 1, 4, negative 3, 2, 16, 2, negative 2, negative 3, 5. Okay. This is like the third time we've looked at this one, right? We already know what the answers are? Yeah? What are the answers? I think Z was 1, right? Y was negative 2, and X was 2, right? That's what we should get. Now, I'd like to do this with the calculator. So everyone who has their calculator that's graphing, I would like for you to go to Let me see. It'll depend on your calculator. You need to get to your matrix menu, okay? You need to go to your matrix menu. In there, you should see something you could, I think, is it math? Hold on, math. Right, math, not edit, not edit, math. Matrix menu and then math. For those of you who have graphing calculator, how many of you have found that? Yes? It should show a bunch of things listed out there. Yes, scroll down until you see something that says R, R, E, F. R, R, E, F. Scroll all the way down. Now be careful, not R, E, F, R, R, E, F. Anyone have trouble finding it? Find R, R, E, F? You found it? Good? Yes? Batteries died? Okay. Everyone else is good? Hit enter, and what that's going to do is it's going to send you back to your home screen, and you should have there on your home screen, I think it's lower cases on the screen. It should have this, and you're sitting there, it's like flashing right here or something, right? Yeah? Yes. Okay. Now, please pay attention. This is where things get a little weird. What we need to do is tell the calculator that we have this augmented matrix. So let me do it above this so everyone can see it. This is how you tell the calculator that this is your matrix. R, R, E, F, parenthesis. All right, here we go. First thing, a bracket. Now your bracket is where?
There's parentheses.
It's the multiplication button.
Yeah.
Yep, above the multiplication button. Okay? So hit your bracket. Now let me tell you what this means to your calculator. What you just told your calculator is that you are going to start a matrix. All right? Then another bracket. This second bracket tells your calculator you're going to start row 1. And now you're going to type in these numbers straight across, all the way across with commas between them. 1, comma 1, comma negative 1, comma negative 1. And make sure you're using some of you have negative keys versus minus keys. Make sure you're using the negative key, not the minus key. What do you think now? Close bracket. What does your calculator interpret that as? End row 1, right? Then what? What do you think? Another bracket. Start row 2. All the numbers with commas. 4, negative 3, 2, 16. Then what? Close bracket. Then open bracket. Then the third row. 2, negative 3, negative 3, 5. Pardon? Oh, negative 2, yes. Thank you. Negative 2 there. Close bracket, ending the third row. Close bracket, ending the matrix. And then finally, be careful with this. Close parenthesis, ending the function. This RREF is a built-in function in your computer. This is that algorithm I was telling you that someone wrote, all right? It has to take on input. It says, okay, here, start, give me the input. Here's the input. Okay, there's the input. Now close the function off. Because maybe after this you want to multiply it by something. Who knows? But, you know, that ends the function. Then hit enter. And you're going to get the reduced row echelon form. You're going to get the diagonal. You're going to get, it depends on how fancy your calculator is. Did it actually look like this? Yeah? Anybody's not look like this? Was it? It doesn't have the line. That's okay. Anyone not get something that looks like that?
Was that weird for you?
Was what weird for me?
Writing those letters in lowercase?
It's a little awkward.
be honest, they're not quite as clean as the
Caps?
Yeah, with all caps.
Yeah. I believe on the calculator it's lowercase, so I'm kind of going with it. So theoretically, all right, those of you who did this on your calculator, theoretically, you could do any system of equations on that calculator. 7 equations, 7 unknowns. You would just have a lot more of these in here, right? That's a good way, especially if you're going to take Cal. I know in Cal 2 we get to a point where we do this problem, and then at some point you run into a system of equations. And sometimes it's 3 equations, 3 unknowns. Sometimes it's 4 unknowns. Sometimes it's 6 unknown. And we don't take time in class to sit here and say, well, how do you solve a system of equations? Oh, remember, elimination. We don't even go through it. We're just like, okay, and then from that you can get the answers. You're like, what? Yeah, that was like a 30-minute process, remember?
Yeah, so
Like it's all just in there.
all the stuff we did in the last 30 minutes in about 20 seconds.
In about 20 seconds, just like here to here. That's it. But if you have your calculator, I know that me, from myself as a Cal 2 instructor, I'm not that big on how my students solve the system of equations. If they do it by hand, then I'm just like, well, I guess they don't know that they can use that fancy calculator sitting right next to them. But if you use the calculator, I'm happier because that means you're actually getting your money's worth out of that thing, All right, so with all that in mind, what would happen if you had a system? I'm not going to give you a new one to do on your calculator. Oh, I should say one more thing about that. I always have students that get all upset with me. They're like, on my calculator, there's a way that I can type in the matrix first, and then come back and I can do the RREF later. And it's people who are familiar with their calculators. The reason why I'm not doing that is because not every calculator has that feature where you can just input the matrix first. And it's a little different with each one, like the TA85 or TA84 is a little different than the TA86 and the 89 and then the Nspire, right? I mean, they're all a little different, but I guarantee you one thing. They all have a matrix menu, a math menu, an RREF built-in function. And the way I put it up here on the board, that can be done with yours, all of them. Okay, so that's why I show that way. All right, so what happens if you had a system that you work through it and you get something like this?
I'd be like, hey teacher, what happened?
Can you solve this?
Sure.
So what does it appear Z is?
3.
Well,
No,
Wait.
no.
0.
Z is 0, right?
Yeah.
Z is 0? So remember what this equation means. That means 3Z equals 0, right? Divide both sides by 3, you get Z is 0. If Z is 0, then this goes away and that goes away, right? And you could go back and solve? Yes? That's not really that big of an issue, but I want you to compare that one to this one. So I wanted you to see these side by side. What does this mean? So I'm comparing these two systems. These are two separate systems of equations. What is this one? What is this last equation telling you? 0 times Z equals 3, which means that 0 equals 3, which is not true, which means that this system is inconsistent, does not have a solution. All right? Doesn't have a solution. That would be the case where we were trying to find the intersection of 3 planes, and they were all parallel. So it would be like first floor, second floor, third floor roofs, right? This roof, the one below, what floor are we on? Third. The one below, right? All those 3 planes never hit each other. This is what would happen when that happens. You get a statement at the end that doesn't make sense. All right? The biggest mistake I see is, students will say, oh, okay, this means Z is 3. No, this doesn't mean Z is 3. This doesn't mean Z is 3 either. Right? What would it have to be here for Z to be 3? 1 and 3, right? You could have 2 and 6, right? But 3 and 9. There's an infinite number of ways it could happen, right?
Or 9 and 20.
Okay, okay. All right, we've got about 20 minutes, so I'm going to introduce you to the next and final topic.
Dun, dun, dun.
We're going into a different chapter. 13. This is really just to expose you to some things that maybe you haven't seen before. So, sequences. This is chapter 13, section 1. So when we talk about, when I say sequence, is there anything you think of? Order? An order of events, a sequence. Fancy dresses with sequence on them?
DNA sequence.
I mean, everyone has a different idea of what that word means to them, right? But if I gave you, let's say, a list of numbers. And I called that a sequence. Would that sit well with you if I just called that a sequence of numbers?
Sure.
Yes? And because it is a sequence of numbers, we usually put a set of braces around it like this. And this right here is an example of a finite sequence. The reason we call it finite is because the actual list stops, right? There are only 1, 2, 3, 4, 5, 6 numbers in that sequence. It's finite. Now I could have done a different sequence like this, but stopped at 100. So instead of writing it, I would put like dot, 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 and then comma 100, like that. And that would still be a finite sequence, wouldn't it? It would have a finite number of numbers in it. But I could also do a sequence where I don't stop. So I put the 3 dots at the end, and the 3 dots just means that that pattern continues forever. And this is what we call an infinite sequence. So we can look at a sequence as really just kind of like a list of numbers. The list might be finite, the list might be infinite.
Why do we say those two words so differently?
How do you say them so different?
Yeah, like why? It's finite and infinite. Why isn't it finite?
All right, I'm not going to get into that part of it. All right, so finite and infinite.
Infinite?
Infinite and finite sequences.
He's thinking now.
Well, I'm thinking of how I'm going to now tell you that a sequence is a function. So we can look at this first sequence up here. Let's just call this first number, let's call it A sub 1.
Here we go.
And then this one, let's call it A sub 2, and A sub 3, and A sub 4, A sub 5, and A sub 6. What?
What about A sub naught? What's that one?
A sub naught? Well, let me tell you about that. Don't be stirring it up today. All right. We always start with 1 with sequences. All right, so here we go. We've got that notation. Is that all right? Yes? Why do we use A? I don't know. That's just the convention. That's the way we like to write sequences. All right, it's just generally accepted. So maybe there's a way that I can come up. Let's focus our attention just on this one. Maybe there's a way that I can come up with a function where what happens is I plug in 1 and it spits out 2. See, because the first number in my sequence needs to be a 2. The second number needs to be a 4. The third needs to be a 6. So the second number needs to become 4. The third becomes 6, and so on. So normally we look at this as a function, right, that does this. It's a pretty obvious function. What is it? What are we doing? Take 1 to 2, 2 to 4, 3 to 6. Just doubling it, right? Just doubling it? So I think most of us would say, all right, if I let f of x be equal to 2x, that should do it, right? But because this is a list of numbers, would it make any sense at all for me to say a sub 1.3? A sub 1.3. Like a sub 1 meant the first number, right? A sub 2 meant the second, a sub 3 meant the third. Like, wouldn't make much sense for me to worry about a sub 1.3. Because I wouldn't have a 1.3 number in the sequence. Does that make sense? You have 1, then 2, then 3. So really, this function only needs to be defined for these numbers, right? 1, 2, 3, 4, for the counting numbers. So what we do is we use a different notation. We don't use x because x makes you think of all real numbers. We use n instead. So I would write f of n equals 2n, where n is a positive integer. In other words, n is what? 1, 2, 3, right? Dot, dot, dot.
Which is a sequence.
Which is a sequence itself, right? An infinite sequence.
Finite, or yeah.
Finite. Infinite. But even this is not the notation we use, all right? I'm just trying to lead us to it, right? We've eliminated x because why?
What?
Why did we eliminate x? What? Because you'll be thinking all real numbers. So I said n, just to get you thinking about something other than real numbers, just the counting numbers. But then instead of f of x, or f of n, we write a sub n equals 2n. So what we do is we get rid of the f completely. The a kind of takes its place. And instead of the parentheses, we just put the n down here as a subscript. This would be the formula right here that would generate this sequence. But I need to stop it, right?
Yes.
So you need to tell me where n is going to stop.
That's it.
At 6. Everyone agree? So for this sequence of numbers, I would say n greater than or equal to 1, less than or equal to 6. This sequence, defined this way, with that restriction on n, will create that sequence.
So do you just put write that up how one says? Do you just want it all boxed up in one?
Well,
Or is there a specific way to write it all? Or just-
Well, you could box it all together if you want. Yeah. I don't think we're at test problem yet. All right, so that would create that sequence. What if I wanted it to not stop? So let me give you this example. Find a formula for this one. And if you use 4 dots, that's okay. 3 dots is the generally accepted.
What if we use 5?
If you use 5, then that just means you really want it to keep going. But it doesn't. I always just I don't even care.
Can you use like 3.6 dots?
You mean like this, 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 and then like just start the dot but don't? Yeah, you can do that. All right, what am I going to use? What's my formula? A sub n is 2n again?
And there are no restrictions. It's 1 less than or equal to n less than.
How about just that? Bigger than 1 or equal to 1. Right? And that would cover it, right? If n is bigger than 1 or equal to 1. So you start out n is 1, then 2, then 3, then 4, then 5, and it creates this sequence, yes? So going back and just trying to reiterate what we have here. If I asked you to graph f of x is 2x, everyone would draw me this line, wouldn't they? That's the function f of x defined on all real numbers. If I asked you to graph this sequence, it's still a function, but it only exists where? At 1, it's, well, I should move this over a little bit. At 1, it's 1, right? And then at 2, it's 4, and then at 3, it's 6. So it's actually just a bunch of black dots, right? That's all it is. And so it doesn't qualify as a function the way that we've been studying functions, right? Our functions have always been nice and smooth, and you can draw them without picking up your pencil. We call them continuous functions. Sequences aren't even close to being functions in terms of what we're used to looking at, but they are truly still functions. It's just our domain is different. The things we're plugging in are only the counting numbers, so the outputs can only be dots. So if we take all the red out, that's your sequence. And also, I don't have a 0, and I don't have anything for negatives. So if you just take all that out, that's your sequence of numbers. Yeah? Seem straightforward? Okay, so how about this? See if you can find a formula for this one. I just want you to raise your hand if you have the formula. I do not want you to yell it out, okay? I don't know if y'all noticed a little while ago, those were the even numbers. Now these are the odds. Except not 1, right? It started at 3. You got it? You think you've got a formula? Okay. If someone else gets a formula, raise your hand and I'll. Okay, got 2, I think 3. 4. 5. See, this is where things start to get a little bit weird in my experience, especially this is in Cal 2. It gets really hard to teach someone how to see something. It gets really difficult. And the people who see it, I always ask them, like, how'd you see that? Well, I don't know, I just saw it. It's hard to teach that. Okay, I think that's enough time. So who wants to volunteer their answer? Raise your hand. You were first, so I'll let you go.
All right, so I got A.
A sub n, that's the way we'd say.
2n plus 1.
2n plus 1. Anyone else?
N is bigger than
Yes? For n is bigger than or equal to 1. So was there any thought process behind that, like that made you think, let's do that? No? You just saw it? Anyone else?
The old number, so it was like 1 more than that.
There we go.
Yeah, that's
All these numbers are 1 more than each even number, right? If you write out the even numbers, 2, 4, 6, 8, all of those were just 1 more than that, right? So if you use the old formula, 2n, you'll create the evens. If you add 1, you'll just add 1 to each of the evens, which creates that. That, I think, is understandable. Yes? So that works. Okay, well. Can I give you another one? We still have 6 minutes. I should be able to get a couple more examples in here. Ready for another one? All right. How about this? Negative 1, 1, 3, 5, dot, 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 dot. Okay. Think so? Yeah? So if someone else volunteer the answer, you want to go, Dave?
Yeah, got A sub n. Wait, hold on,
You should have wrote it down.
3.
Go ahead.
Okay.
2n minus what? 1?
3.
3, 1? What do y'all think? It depends on where you start, but we are always going to want to start at n as 1, so 3. So again, what you have to kind of see here is that these are all odd numbers, right? So it's going to be 2n creates the evens. So if you take all the even numbers and you shift them to the left 3. So imagine your even numbers, 2, 4, 6, 8, 10. I actually want to create a negative 1. So don't I have to take 3 away from that? And then take 3 away from that? And 3 away from that, and 3 away from that, so on and so forth. Yeah? Okay? All right.
I was just happy with that.
That will work. Good. How about this? Four sevenths.
All right.
6 ninths. I'm not going to reduce these fractions if they do reduce. 8 elevenths, dot, dot, dot. I'm going to help you through this one. When you have fractions, try and focus your attention on the numerator and denominator separately. Do you notice anything in the numerators? 4, 6, 8, those are all evens starting where? At 4, right? So how do I create the evens starting at 4? 2n plus 2. So 2n would start the evens, right? That would be evens starting at 2. But I want it to start at 4, so I move it over by 2. And then the bottom are all the odds starting at 7. 2n. Well, this is going to give you what? If I let n be 1 here, what am I going to get? 2? I need to be at 7. 5. That'll create it, won't it? Still have 2 minutes. How about this one? 2/3, 4 ninths, 8 27ths, 16 81sts. You see it? Okay, hold on.
And, well, 2 and 3, no,
Y'all are thinking out loud here. What are the numerators?
it's 2n over 3 to the nth power.
Is the top 2n?
No, well, it's
Yes.
n squared.
Where's 6?
And,
It's n squared.
wait, yeah.
Because 1 squared is
1 squared is not 2.
I don't know.
Plus, no.
I thought I saw it. I guess I don't have division.
You got just 2 minutes.
2 to the first, 2 squared, 2 cubed, 2 to the fourth. Isn't it? The bottom, 3 to the first, 3 squared, 3 to the third, 3 to the fourth, right? What's never changing in both the numerator and denominator? The bases, right? 2 and 3. what keeps changing are the exponents. And they keep on going up by 1, right? So couldn't I write this as 2 to the n over 3 to the n? And isn't that the same as 2/3 to the n? Would you like a little bonus one to take home? Okay, I'll give you a bonus one. See if you can find a formula for this. To be turned in at the beginning of class next time.
And this is bonus or?
For bonus, yes.
Like how much bonus?
The fewer people get it, the more it's worth. It's inversely proportional to the number of people that turn it in.
Gotcha.
Okay? So if everybody turns it in, then obviously it wasn't hard enough.
2 points off of it, or
All right, here we go.
Mm.
5 over 4. 8. Oh, negative 8 over 16. 11 over 64. Negative 14 over, what is that? Got to make sure I get my math right here. I don't want to send you with something that's not going to work. Yeah, 256.
So you're just making this up, right?
Yes.
am I making?
I can't even blame it on the book now. It's just,
All right, so the biggest thing I want you to notice about that is that your sequence is switching signs. Like your first one is a positive number and then the second one is negative. Your formula must account for that. So that's why it's a bonus. You have a good day. See you on Wednesday, our last day of class.